All right, welcome back. We are here for another edition of Calculus 1, the stay-at-home series. And we are going to talk about section 4.5. I told you that we would jump from 4.1 to 4.5 because optimization is an application of the extreme value theorem. Most of the time, functions are being optimized. We are optimizing them on a closed interval, and so we can apply the extreme value theorem to that. And optimization, guys, is probably the number one, outside of statistics, the number one area in which applied mathematics is used in industry and business and in pretty much all business that is trying to make a profit. And the reason for that is because optimization is exactly what it sounds like. It's trying to get the most or the least depending on the situation, right? So we want to get the most profit out of a particular run of our machinery. We want to make the minimum expense in that. We want to minimize the amount of time that it takes for us to deliver all of our packages. We want to maximize the volume of packages we can fit together in our delivery van. So maximizing, minimizing is something that we do consistently in the real world, in businesses all over the place. The more that we understand data and the more that we understand mathematics, the more that we're using it to optimize our financial situations in business. And you can do that for your own personal life as well. But really the idea of maximizing and minimizing a function, right, is just an application of the EVT. So that's the idea of optimization. And I'm going to show you an example of how it works if you already have the function. If the model has already been created for you, okay, if the model's already created, then there's nothing more to do than what we did in section 4.1, right? Just do the stuff. So how did we do optimizing in 4.1? Notice we have for the first 12 hours. So what does that mean is our closed interval, 0 to 12, right? If T is the number of hours after consumption of alcohol, then 0 to 12 is our closed interval. Here's our continuous function. So what's the first step? Take the derivative. If you notice, you have you have 0.12t, 0.12t, e to the negative 2 t over 2, and so that is a product rule. So we take the derivative of the first, which is just 0.12 times the second plus the first 0.12t times the derivative of the second, which is e to the negative t over 2 times negative 1 over 2. 2 is a constant, and so we don't think of this as a quotient. We think of this as 1/2 t. And so we get the negative 1/2 here. So that's step one, is to take the derivative using the product rule here and the chain rule involved for the e. Step two is what? Set this equal to 0. And when we set this equal to 0, we have some stuff in common. And so let's put that in purple. We'll take out the common factors of 0.12 and e to the negative t over 2. That's the common factors. And we factor those out. And here, we're just left with a 1. Here, we're left with a t, and we're left with a negative 1/2. Okay, and so now we need to set these each individually. Since we're in factored form, we need to set these each individually equal to 0. This is 1 plus negative t over 2 equal to 0 if I multiply those together. And then here, remember that e to a power is never 0. E to a power is positive always, and so therefore we do not have anything contributed here. We don't have any critical numbers here. If we take a look at this guy on the right hand side, we get 1 equals t over 2, and so that means 2 is equal to t. So 2, which is clearly in our interval from 0 to 12, 2 is our only critical number that we have for this scenario. So now step 1 is to take the derivative. Step 2 is to set the derivative equal to 0. Step 3, and our last step, is to do the candidates test. We take P and we evaluate it at 0 and at 12 because that's where our endpoints are, 0 and 12. And then we also need to plug in 2, right? And so our formula is 0.12 times T times e to the minus T over 2, 0.12 times T e to the minus T over 2, and 0.12 times T e to the minus T over 2. So this guy's 0, obviously. If you haven't drank anything yet, then you don't have any alcohol in your system, we hope, right? After 12 hours, if we type in 0.12 times 12 times e raised to the 0.12 times 12 times e raised to the negative 12 divided by 2 power, then we end up with 0.036, and that's also very small, as you might expect after 12 hours. And finally, if we put in 0.12 times 2 and then multiply that by e to the negative 2 over 2, then you end up with 0.0, well, how did I get that on there? There we go, 0.088, all right, almost 0.09, and that is the level of, that's the percentage of alcohol in the blood. So as a percentage, that's 0.088%. All right, this is not the same thing that we would use, that the police use. They use a different system, but anyway. So that is obviously the maximum amount, and that maximum happens after 2 hours. Okay? So the process, once you have the equation, the process is exactly the same as we did back in section 4.1. So because of that, right, I want to focus mainly on the problems that involve us having to do the formula ourselves, where we have to find the formula, okay? So the process that you need to do, this is what we'll call the setup, right? You can handle everything else. This is what we call the setup. And so the setup is this. We have usually 2 expressions to deal with. We have the first thing, which is called a primary function, right? And some textbooks would call this the objective function, right? Objective being the object of the problem. In other words, we want to maximize the revenue, then revenue is our primary function. We want to minimize the amount of material needed to build a fence, then the amount of material to build the fence is the primary function. And then we have a secondary thing, which is often called this, which is called a secondary. We have a second expression, secondary equation, sometimes called the constraint equation. Okay, in higher level optimization, oftentimes we might have more than one constraint. But for right now, we've got just one constraint that we're going to be working with. So all of our problems in section 5 will have this process if we don't know the function yet. All right, and so here's the deal. The primary function, the objective function, it's called a function because this is what we want to maximize or minimize. We want to get the max or min for this. Okay? This is called an equation and not a function because this is a fixed number. This is a fixed value. All right, so for example, if I tell you I have 1,000 feet of fence to use to enclose a field, then 1,000 feet can't be maximized. 1,000 feet is 1,000 feet is 1,000 feet. You want to maximize it, use it all. So that is not what we would be trying to maximize. That would be a constraint. We only have 1,000 feet of fence. If we had more fence, we could make a bigger field, a bigger rectangle, right? And so it's very, very important when you're reading the problems that you can identify which of these is primary and which of these is secondary, okay? And then draw some pictures, just like other word problems, draw a picture, try to figure out what's going on if it makes sense, okay? But for sure, you want to determine which one's your primary function, which one's your secondary equation. And then what we do for us, okay, in this section, this is not always the case, but in this section, here's pretty much what's going to happen. There will be two variables, length and width, all right, cost and amount of items, something like that. There will be two things that we have. There's two variables we don't know. So what we do is we use the secondary equation to simplify the primary function I'm much better at writing on the board than I am writing on this thing. Then simplify the primary function into having only one variable. Right? We're not in Calculus 3. We can't do a function of multiple variables. So, and this is not related rates. And so we do have a primary objective function. And so we need to be able to do the calculus from 4.1, finding the derivative, setting it equal to 0, finding the critical numbers, and testing those endpoints and stuff like that. We need to be able to do that process, and the only way to do that is we have one variable. Okay, so let me show you a couple of examples of the type of thing that I'm talking about. I am not going to necessarily work all the equations all the way out. I am going to get you to the setup. Okay, so that's what we're going to focus on for the next 10 minutes or so is the setup. Example 1. Okay. A 12-ounce can of Coke has a volume of 255 cubic centimeters. That's volume. Okay. If the can is to be in the shape of a cylinder, find the dimensions of the can that minimizes the amount of material needed. The surface area is the amount of material, right? The surface area of the can. Now, this is a simplified problem. A Coke can has different aluminum that goes on the top and the bottom versus the sides, but we're not going to worry about that. We're going to assume this is all the same stuff. So the volume of the cylinder formula is given to you, and the surface area of a cylinder is given to you. Okay, so you've got your Coke can. Excuse me while I do a rudimentary drawing here. Your Coke can here. All right, this is your height of your Coke can. Your radius is that thing right there. And so these are the things that come up in your volume and in your surface area, right? Volume's pi r squared h. I don't expect you to know these formulas. You don't have to memorize them. I'll give them to you if you need them. Area is 2 pi r h, which is the circumference all the way around. That's the sides. And then 2 pi r squared. Area of a circle is pi r squared. There's a top and a bottom, so that's where the 2 pi r squared comes from, right? So you've got both volume and surface area. So now the question is, which one's primary and which one's secondary? Well, how do you tell? One way to tell is, what are you trying to minimize? Are you trying to minimize the volume, or are you trying to minimize the surface area? According to this, you're trying to minimize the surface area. So this must be your primary function. Another way to know is the fact that they tell you the volume of a Coke can is supposed to hold 255 cubic centimeters. It's a 12-ounce can of Coke. It's not a 20-ounce bottle. It's not a 2-liter bottle. It is a 12-ounce can, and that holds 255 cubic centimeters. So that is fixed. That's secondary. Okay? So your primary function, therefore, is this area function, which, as we recognize and as we mentioned, would have two variables, has r and has h. You have your secondary equation, which is volume, but the volume is a fixed amount, 255 cubic centimeters, and that's supposed to be pi r squared h. So what we're going to do is we're going to take this and we're going to solve for one of the other variables, for one of the variables. Well, it's up to you which one, but I'm going to tell you that in this case, there's a very clear choice, and that is I want to solve for h. H pops up once, r pops up twice, and one time it's squared. So I would really rather not plug in for r. I would really much rather plug in for h. So we're going to solve this for h, which is simply dividing both sides by pi r squared. And so we end up with 255 divided by pi r squared, and that equals h. Okay? So this is the relationship that our secondary equation gives us that allows us to simplify our primary objective function. Okay? So what we're going to do is we're going to substitute now this variable h. If you told me h equaled 3, I'd stick a 3 in there. You're telling me h equals this, so I'm going to stick that in the h spot. Okay? So our primary function is a, and it's going to be in terms of r only now. A of r is 2 pi r times what? Times h, but h is 255 over pi r squared, so we plug that in there, and then we still have the other part, the plus 2 pi r squared. All right, obviously if we want to work with this guy, we're going to simplify it as much as we can. We can divide the pi away, and we can divide one of the r's away. And so this turns out that our primary function a of r is 2 times 255, which is 510 over r plus 2 pi r squared. This is my a of r function. Okay, so this is the setup. This here, if you'll indulge me for a second here, let me scroll back and let me fix the U. All right, this is what I called the setup. So all of this work that we've done, this is getting us to the point where we were back here in problem number 1. See, this was my P. This is my primary function right here. Okay, and so that's my primary function, and I'm ready to go, right? So all of that work that we just did was to get us to our primary function. Now, step 1, step 2, step 3, take the first derivative, find the critical numbers, blah, 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 blah. Okay? Now, it turns out that this particular function doesn't have a closed interval that it's on. And so, again, I told you I wasn't going to solve these problems. There's a slightly different way you have to do the solving part of this, and that is you don't have the candidates test. But we're not going to worry about that right now. But I'm just worried about how you set problems up. Okay, I'm interested in you setting up the problems. So let's try another one. I made this example 1. This really wasn't example 1, right? This was our second example. It was our first example with this type of process. Here's another example. Example number 3 now. Alrighty. So now for problem 3, we're going to do the same kind of thing. We need to draw a picture here. We've got Farmer Bob with 200 feet of fence, and he wants to do a rectangular area next to his barn. And so he's got this barn here, which is 30 by 20. And so we're going to draw it out here where this is 30 feet here on the side and 20 feet wide. And then let's do the fence in green or something different. And so he's going to build the fence off of that barn so that his animals can get from the barn out into the field here. Okay? And so what that means is, you know, I've got stuff here that I don't know what these are. I don't know the length and I don't know the width. And that's a rectangle. And so I'm going to label them using variables. This is the width of my field. This is the length of my field that I'm enclosing in this fencing. And then so that means that this side is not L, because this side, 30 of the feet on this side of my rectangle, this side has to be the same as this side. This side of my rectangle, the length of my rectangle is not going to use fence around the barn. That doesn't make any sense. We already have a barn, right? So this is going to be 30 feet less. And over here, this is going to be 20 feet less. And so we have W minus 20 and L minus 30 for these sides, okay? So now, we're looking for our primary function and our secondary equation. What's primary? Well, what are we trying to find? We're trying to find the maximum area. Find the maximum area. Immediately, that tells me that area is my primary function if I want to maximize it. But how do you find the area of a rectangle? It's just length times width. Simple enough. Well, then what does that mean is left to be the secondary equation? Remember, secondary equations are constraints. They are what we are constrained by. Well, we're constrained by the amount of fence that we can use. We have all this fence. If we had more fence, we could fence in a bigger area, but we don't. We have what? 200 feet of fence. So we have 200 is our secondary amount. That's what? That's going to be the perimeter of the fence. Now be careful. If you're doing the perimeter of a rectangle, right, there's a geometric formula for that. It's 2L plus 2W, but we can't use that because this side and this side do not take up the entire length L or width W, right? So just go all the way around the fence, starting right here. If we go all the way around the fence, how much fence is on the left here? We use 200 feet of fence. We're going to use W minus 20 plus L plus W, and then the top part of the fence here is L minus 30. So it's not 2L plus 2W, it's 2W plus 2L minus 50. We have the minus 20 and the minus 30 that we combine. And so if we solve the, or if we if we add 50 to both sides, right, then what happens is we get the secondary equation is 150 equals 2W plus 2L. Okay? So we now have what we had back in our previous situation. We had a primary that has two variables and a secondary that has two variables. But because the secondary is equal to a constant, we can solve for one of the variables. Now, last time it was very obvious which variable was a better choice. This time, not so much. In fact, it doesn't matter at all. You can solve for W or you can solve for L, your choice. I feel like most students would solve for L, and I could be wrong, but I'm going to do that anyway. And so 2W, subtract 2W from both sides, and we get 150 minus 2W equals 2L, and then divide everything by 2L, and so the 2's will cancel here and divide that away, and so we have L is equal to 75 150, not 150, 250. Golly, 250. Glad I caught that. That's too big. All right, so this is 250, not 150. And so that gives us 125 minus minus W. Let me write that over. If we divide both pieces here by 2, we get 125 minus W. So what do we do with L equals 125 minus W? We plug it in. Get your area function in terms of L only. So area is going to be in terms of L. We get L times W. W was given to be 125 minus what the L? This is not L, this is in terms of W, right? We solved for L, so we're going to plug in for L, which means we're doing a W here. We're plugging in for L, we're going to have W left. So L is 125 minus W, and then we're going to multiply that by W. That's going to be our equation. So this is why you don't make videos late at night after you've been working on the computer all day. So you get 125 W minus W squared, and that is our primary function, folks. Okay, so what do we do with that? This is kind of the end of the setup. This is, again, this is what was given to you in problem number 1. Now, I am going to go ahead and solve this one out because the algebra is a lot simpler, and I want you to see what happens because you have to find your endpoints, and we haven't done that yet. Okay, so our area function in terms of W is 125 W minus W squared, or if you're like me from West Virginia, it's 125W minus W squared. W is how you pronounce this letter in West Virginia. Don't ask me why, but that's the way it works. So take the derivative, right? This is all the 4.1 stuff. This is all the stuff you're supposed to know how to do real well by now. Take the derivative, 125 minus 2W. Set it equal to 0, 125 minus 2W. Add 2W to both sides. Divide by 2. And you get W equals 62.5. And so that's one of your candidates. That's your only critical value, only critical number. And we have to make sure it's inside of our interval. Oh, crud. We don't have an interval. We need a closed interval for the EVT to work. And that's the way we've only ever done the candidates test, is to have a closed interval. And in fact, that's the only way to do the candidates test. Again, there is a way that you can optimize things if you don't have a closed interval. And we're not going to worry about that a whole lot. But if we go back to our picture, what's the smallest that W can ever be? W can't be 0 because you've got this fence over here. You've got this barn that you've got to connect to. And so we've got to have at least 20 feet of W, because that would make W minus 20 equal to 0. So the smallest W could ever be, right, would be if you didn't have any fence over here past the barn, then W would still have to be 20 feet. Everybody with me on that? Okay? You would still have to have 20 feet there. So because of that, our lowest possible value for W is 20. Now, what about the biggest possible value? Well, remember that L was equal to 125 minus W. What's the smallest that L could be? The smallest L could be, by a similar argument, would be what? If L was equal to 30, then we'd have this much fencing and you wouldn't have any extra fence beyond the barn. So L equal to 30 is the smallest it could be. If we solve this for W, that would tell you W equal to 95 is the largest that W could be, because that coincides with the time that the L is its smallest, okay? So we do have our 3 candidates to test, but you had to find, this is called the effective domain, based on, right, there's a whole bunch of numbers you could plug in for W here. In fact, as a model, W could be any real number. This is just a polynomial. But for our word problem, it only makes sense if W is between these two numbers. That's why it's the effective domain. So we restrict our A to these W's. And so now we do our candidates test. We do A of 20, we do A of 95, and we do A of 62.5. All right, and so I'm going to zip these out real quick here. If I multiply 125 times 20 minus 20 squared, remember I'm plugging into the original function because we're doing the candidates test. All right, if I do that, I get 2100 square feet. Okay, or I can use FT with a square over it. If I do 125 times 95 minus 95 squared, I'm not going to write it down, then you'd get 2850 square feet. And then, of course, if you take 62.5 as your W, you take 125 times 62.5 minus 62.5 all squared, and you would end up with 3,906 feet, 0.25, 3,906.25 square feet, and that is by far the largest. Okay, so that's your max area. Now, what did the question originally say? The question originally said, find the dimensions that give you the maximum area. How do I find the dimensions? Well, I have to take L. L was equal to 125 minus W. Plug in this for W, and you get 125 minus 62.5, which is, again, 62.5. And so the dimensions that yield this maximum area for Farmer Brown's fence here is 62.5 feet by 62.5 feet. So you can see that even if you had decided up here to solve back here, if you had decided to solve this equation here for W instead of L and plugged in and had an A of L instead of an A of W, you would have ended up with the same thing as your answer. Okay, so that is optimization, and hopefully, in a nutshell anyway, and hopefully you guys can play around with the MyMathLab and stuff like that, but guys, it takes practice, lots of practice to be able to get these primary and secondary equations, secondary equation, primary functions, kind of get used to doing those, all right? Again, any geometric formulas I'll give you, but other things that are not are given, make sure you draw the picture out and figure it out for the problems, okay? Lots of practice and you'll get this. You got it, all right? Thanks.